So, we are again we are back, right. So, this is actually second order system. Now, the state matrix A is equal to this much, whatever we have got here, this is my state matrix. So, the eigenvalues of the state matrix can be written as, I mean you have to set determinant 0. So, minus 0.143 kd minus lambda minus 0.108, then 377 minus lambda, the determinant of this one is equal to 0, right. I mean your A minus determinant of A minus lambda is equal to 0, right. So, if you simplify this equation, it will be lambda square plus 0.143 kd lambda plus 40.79 is equal to 0. If you simplify, it will come like this, simply quadratic equation, right. Now, this equation is of the form of, we can write lambda square plus 2 xi omega n lambda plus omega n square is equal to 0. I mean this equation we can put it like this. So, if you compare, then with omega n square, here it is, we have made omega n square is equal to 40.79. So, omega n is equal to root over 40.79, that is 6.387 radian per second, right. And if you divide by 2 pi, then f n is equal to natural frequency will be 1.0165 hertz, right. And 2 xi omega n is equal to nothing but 0.143 kd, right. And first we have to see kd is equal to 10, 3 values are given, kd is equal to 0, kd is equal to minus 10 and kd is equal to plus 10. We will take first kd is equal to plus 10, right. So, and 2 xi omega n is equal to 0.143 kd or xi is equal to 0.143 kd upon 2 omega n. So, omega n we have got it 6.387, therefore, xi is equal to 0.143 kd upon 2 into 6.387, and this comes actually 0.0112 kd, that is equal to xi, right. Now, in terms of kd, if you put kd is equal to 10, it will be 0.112, if you put kd is equal to 0, then xi will be 0, if you put kd is equal to minus 10, it will be minus 0.112, right. So, eigenvalues are lambda or lambda 2, it can be written as minus xi omega n plus minus one thing is there, that is your j is missed, right. So, minus xi omega n plus minus j omega n root over 1 minus xi square, right. So, the damped frequency is that omega d is equal to omega n root over 1 minus your xi square, that is this one, right. And so, I have corrected that one, and now for kd is equal to 0, 10 and minus 10, that lambda will be like this. So, when kd is equal to 0, lambda will be, it is a 2 into 2 system, only 2 eigenvalues. So, lambda will be 0, real part is 0 plus minus j 6.39. Now, when kd is equal to 10, it will be minus 0.714 plus minus the complex conjugate pair j 6.35. If kd is equal to minus 10, it is 0.714 plus minus j 6.36. That means, with kd is equal to minus 10, actually system becomes unstable. Now, with that, if you calculate omega d, so it is 1.0165 hertz when it is kd is equal to 0, but when it is 10 or minus 10, it will remain same 1.0101 hertz, it is also 1.0101 hertz, right. And for kd is equal to 0, xi will be 0, here it will be 0.112 and here it will be minus 0.112, and omega n will be all this case 1.0165 hertz, 1.0165 hertz, 1.0165 hertz. So, these results are given in tabular form, right. Now, part B, the right eigenvectors are given by, that is A minus lambda I into phi is equal to 0. This we have also seen to get this at the beginning, the right eigenvector, left eigenvector, right. So, if you get the right eigenvector, you will get the left eigenvector also. So, from the given system with kd is equal to 10, the above equation becomes, when kd is equal to 10. So, this equation, I mean this A minus lambda I into phi, it becomes that minus 1.43 minus lambda I minus 0.108, 377 and minus lambda, and here it will be phi 1 I, phi 2 I, right. This is for your what you call for ith eigenvalue, say, right, for is equal to 0, but kd is equal to 10 means we will consider this eigenvalue, right. So, now for lambda 1 we are considering your positive imaginary part, that is minus 0.714 plus j 6.35. The corresponding equations are, if you assume lambda 1 is equal to this and write down the equation, right, then you will get for I is equal to 1, because I is equal to 1 means, and there should not be any confusion, this is lambda 1 the first eigenvalue, that means I is equal to 1, right. So, that is why this this is phi 1 1 and this is phi 2 1. We have written phi 1 I, phi 2 I is equal to 0, right. So, that is phi 1 1, phi 2 1. So, if you write this equation, this is that means for I is equal to 1, this is phi 1 1, this is phi 2 1, that means minus 1.43 minus lambda I into phi 1 1 minus 0.108 into phi 2 1 is equal to 0. This is one equation, right. So, your what you call I mean if you simplify, this will be plus, because here it is minus is here, minus both the cases it is minus is here, here it is minus is here. So, ultimately it will become 0.714 plus j 6.35 phi 1 1 plus 0.108 phi 2 1 is equal to 0. This is one equation. Second equation also 377 phi 1 1 plus I mean this one 377 phi 1 1, right. I mean this equation, that is phi 1 1, right, and your lambda 1 is equal to minus 0.714 plus j 6.35. So, this one become actually plus 0.714 minus j 6.35 phi 2 1 is equal to 0. These two equations first you write down, right, first you write down these two equations. Equation numbers are not given, but we have written this one, but above equations are not linearly independent, right. One of the eigenvectors corresponding to an eigenvalue has to be set arbitrarily. I mean phi 1 1 and phi 2 1, you have to choose one of them arbitrarily, right. Therefore, we assume that phi 2 1 is equal to 1. This is normal practice, such that calculation will be easier for this small problem. So, if you choose phi 2 1 is equal to 1, then you will get your what you call that phi 1 1 will become minus 0.0019 plus j 0.0168. This is phi 1 1, right. Similarly, eigenvector corresponding to your psi 2 lambda 2, that is second eigenvalue, minus 0.714 minus j 6.35. That means here I is equal to 2, right, I is equal to 2. That means, if you go back to that equation, for I is equal to 2, here I is equal to 2 means phi 1 2 and this is phi 2 2 and this will be lambda 2, right, because I is equal to 2 means this will be lambda 2 and lambda 2 is equal to, we have taken this one minus 0.714 minus j 6.35, previous one was plus j 6.35, this is minus j 6, and you substitute, and if you substitute and if you just your what you call that assume phi 2 to 1, similarly similarly your what you call like this like this, you please write the other two equations in terms of 2 1 and 2 2, you write down the other two equations, right, for that lambda 2 values, and then you assume that phi 2 2 is equal to, I think we have assumed phi 2 2 is equal to 1, right, that is phi 2 2 is equal to 1, then phi 1 2 can be calculated minus 0.0019 minus j 0.0168, right. So, we got all the 4 values. Therefore, we will go to the next page. So, just hold on. Right. So, right eigenvector modal matrix is phi is equal to, then given as phi 1 1, then phi 1 2, then phi 2 1 and phi 2 2. This is my phi, right. This is that right eigenvector modal matrix. Now, we know phi is that, you know that your phi psi phi, that is your is equal to 1 in general. We have seen that psi I phi I is equal to 1, or in general psi phi is equal to I, the identity matrix. Therefore, psi is equal to phi inverse, that means, if you take the inverse of this one, you will get the left eigenvector. So, psi is equal to, if you take the inverse of this matrix, it will come like this, that minus j 29.76 and 0.5 minus j 0.056, right, and this one also j 29.76 and 0.5 plus j your 0.056. So, this is left eigenvector, right. Now, we got right eigenvector, we got the left eigenvector, right. So, time response is given by earlier we have seen in general. So, delta omega r t delta t will be phi 1 1, phi 1 2, phi 2 1, phi 2 2, then C 1 e to the power lambda 1 t, C 2 e to the power lambda 2 t. If you go back to that equation, that your time response of delta x, we wrote in terms of phi and C 1 for a particular variable I, but here you have two variables, that is one is delta omega r and another is delta t, right. So, that is why putting this one, first one phi 1 1 C 1 e to the power lambda 1 t and phi 1 2 C 2 e to the power lambda 2 t. Similarly, for I is equal to 2, the second variable, that is your delta t, phi 2 1 C 1 e to the power lambda 1 t plus phi 2 2 C 2 e to the power lambda 2 t, right. So, this is that general expression for your, I think slowly and slowly your understanding will be clear, right. So, this one, if it is so, then at t is equal to 0, these initial conditions are given, that at t is equal to 0, that delta is equal to given 5 degree is equal to 0.0873 radian, and delta omega was also given initial condition 0. Therefore, we have seen in general that C is equal to your psi delta x 0, that was that C I, I mean in general we have seen that initial condition, this C I is equal to your what you call that psi I, then delta x I 0. This way you saw the initial conditions, right, but that was mathematics, that is representation of this one, but in general actually C 1 and C 2 you can easily put it in your mind, it is left eigenvector into delta omega 0 delta. Easy to remember is that C 1 C 2 or C 3 whatever may be the number of state variables, it will be your left eigenvector. So, psi 1 1, psi 1 2, psi 2 1, psi 2 2 into that delta omega 0 delta omega 0 delta 0. This way you can put it in your memory, the way it has been given in the mathematical form, right. If you do so, then it will become that your psi, we got this matrix, that psi matrix, the left eigenvector. So, it is minus j 29.76, 0.5 minus j 0.056 and this is j 29.76 and it is 0.5 plus j 0.056 and initial value at t is equal to 0, delta omega 0 and delta is 0.08 say your 73 radian. So, we put these values and just simplify, then you will get C 1 is equal to 0.0436 minus j 0.0049 and C 2 will get 0.0436 plus j 0.0049, right. Therefore, the time response of speed deviation is given by from this equation, right, from this equation that your delta omega r t is phi 1 1 C 1 e to the power lambda 1 t plus phi 1 2 C 2 e to the power lambda 2 t. You substitute the value of phi 1 1 C 1 and lambda 1, right. So, it will be in this form, that very complicated form, that phi 1 1 is this much minus 0.0019 plus j 0.0168 and C 1 is this much 0.0436 minus j 0.0049, then e to the power lambda 1 is minus 0.714 plus j 6.35 into t plus that your phi 1 2 minus 0.0019 minus j 0.0168, right. Then your C 2 0.0436 plus j 0.0049 e to the power minus 0.714 minus j 6.35 t, right. So, this is response of delta omega t, time response. If you simplify this one, if you just hold on, if you simplify this one, you will find that how response will come, and if you simplify, it will come in this form, delta omega t is minus 0.0015 e to the power minus 0.714 t into sin 6.35 t. I mean, if you simplify all these things, you will find there will be no complex number involved, right, nothing will be there, and whatever I am giving, this answer is correct one, right. But all derivation cannot be put here, then it will consume lot of time, but this is the form for delta omega t, that minus 0.0015 e to the power minus 0.714 t into sin 6.35 t. As a check, at t is equal to 0, this sin term will become 0, therefore, delta omega at t is equal to 0 will become 0, right. Similarly, the time response of the rotor angle deviation, right. Similarly, delta I mean here from this equation, that delta t is equal to phi to 1 C 1 to the power lambda 1 t. I mean, I have given the final form only, but if I write on this, delta phi t will be phi to 1 C 1 e to the power lambda 1 t plus phi to 2 C 2 e to the power lambda 2 t, right. So, if you put phi to 1 value, C 1 value, lambda 1 your what you call lambda 1 value, phi 2 value, C 2 value and lambda 2 value, then you will get response for the delta, right. Now, therefore, similarly, delta you will get 0.088 e to the power minus 0.714 t cosine of 6.35 t minus 0.11 t. Now, if you put at t is equal to 0, you will find delta at t is equal to 0 will become 5 degree, or what you call that we have converted to the radian 0.0873 radian, right. From that you can make out that your response is correct. So, this is delta t and this is your delta omega t, the time response, right. So, from that you can make out that this response actually is stable, right. So, this is a second order system with an oscillatory mode of response having a damped frequency of 6.35 radian per second. Every term delta or delta omega t attached basically with a sinusoidal term multiplied, right, or 1.0101 hertz. The oscillation decay with a time constant 1 upon, I have not calculated it, that 1 upon your 0.714, right. So, it will be roughly approximately 1.31 or 32 second. I did not put it, I missed it actually, right. So, because your that e to the power minus 0.714 is coming. So, with a time constant will be 1 upon 0.714. So, roughly 1.3 or 32 second, right. This corresponds to a damping ratio, that xi is equal to 0.112, right. So, just hold on. So, if you I mean from this thing your what you call, from this thing you can find out the time constant, right. You know that it is basically e to the power minus t upon tau, right. So, it is 1 upon 0.714 whatever it comes, right. Next is that mode shape sensitivity. This is an example. I will take some other example. Mode shape, sensitivity and participation factor. Now, mode shape and eigenvector. Suppose x is equal to phi z, right. Earlier also we have taken like this. Now, therefore, we can write x t is equal to phi into z t. So, therefore, x t is equal to phi 1, phi 2, phi n z t. This is say equation 31, right. So, this is nothing, this is just hold on, this is actually nothing, this is for my own reference, right. So, we can, and z t is equal to psi x t, this is also we have earlier we have seen, if z t is equal to psi x t, then mathematically it can be written as z t is equal to psi 1 transpose psi 2 transpose up to sin transpose to the transpose x t, and this is actually not a vector, it is a matrix, because each one is a your what you call that column vector, right. This is equation 32. Now, the variables x 1, x 2, x n are the original state variable chosen to represent the dynamic performance of the system, this we know, and z is the transformed variable, right. The variable z and z1, z2 and zn are the transform state variables, such that each variable is associated with any one mode. In other words, the transform variable z are directly related to the modes, right. From equation 31, we see that the right eigenvector gives the mode shape, that is the relative activity of the state variables, right. That is from equation 31. That means, from this equation and phi is actually the right eigenvector, right. So, from equation 31 we see that right eigenvector gives the mode shape, that is the relative activity of the state variable when a particular mode is excited. For example, the degree of activity of the state variable x k in the ith mode is given by the element phi k I of the right eigenvector phi I, right. That means, the magnitudes of the element of phi I give the extents of the activities of the n state variable in the ith mode. Later we will see this exactly what its meaning, and the angles of the elements give phase displacement of the state variable with regard to the mode, right. So, as seen from equation 32, that means this equation, this is function of actually your left eigenvector, right. So, from equation 32, right, the left eigenvector psi I identifies which combination of the original state variables displays only the ith mode. Thus, the kth element of the right eigenvector phi I measures the activity of the variable x k in the ith mode, and the kth element of the left eigenvector psi I weighs the contribution of this activity of the ith mode, right. This is the meaning. Now, that eigenvalue sensitivity, from this thing slowly and slowly we will go to the participation factor. Now, examine the sensitivity of the eigenvalues to the elements of the state matrix. Consider equation which defines the eigenvalue and eigenvectors. Actually, this is actually equation number, I forgot to write. Previously we have taken that that in the dynamic system, maybe just it is equation, this equation is rewritten here, of course, right, that your this equation, that a phi I is equal to lambda I phi I, right, this is this equation. So, differentiating with respect to a k j, the element of a in the kth row and jth column. Suppose you have the matrix, now things will be clear to you, just hold on, right, just hold on. Suppose you have the matrix, right, you have the matrix. So, it is actually spelling that a k j, that is in the kth row. Suppose a 1 1, a 1 2, a 1 2 up to a 1 n, then suppose it is a k 1, a k 2 up to a k n, right, that is a kth row, and suppose it is coming a n 1, a n 2 up to a n n, right, it is kth row, and say some jth column, somewhere a 1 1, a n 2, a k 1, a k 2, some element say k, a k j. So, this is the thing, and this is the your kth row and your jth column. So, this is your say a k j, right. So, and if you take the derivative of this one, then this equation, if you take the derivative a phi I is equal to lambda I phi I, then your it will be delta a k j phi I plus a into delta phi delta a k j. This is the left hand side, right, is equal to the right hand side. If you look into this, delta lambda I upon delta a k j phi I plus lambda I into delta phi upon delta a k j, right. Now, pre-multiplying by psi I and noting that psi phi is equal to 1, we know identity matrix. So, psi I phi I is 1 and psi I a minus lambda is equal to 0. So, this we have seen it before, right. So, multiply both sides by psi I, this equation. So, if you do so, it will be psi I delta a upon delta a k j phi I plus psi I a delta phi upon delta a k j is equal to psi I delta lambda I by delta a k j phi I plus psi I lambda I delta phi I upon delta a k j, right. Now, upon simplification you will get this, that psi I delta A upon delta A k j phi I is equal to psi I phi I delta lambda I upon delta A k j minus psi I A minus lambda I into I, that is identity matrix bracket close delta phi I upon delta A k j, right, or psi I delta A upon delta k j phi I is equal to delta lambda I upon delta k j, because from this definition we know psi I phi I is equal to 1, and from this definition this one we know 0 and this one we know it is equal to 1 and this is 0. Therefore, psi I delta A upon delta A k j phi I is equal to delta lambda I upon delta A k j, right. Now, let me clear it. Equation number I have not given here, but I think it is understandable for you. Now, all elements of delta A upon delta A k j are 0 except for the element in the kth row, right. So, because we have taken that derivative with respect to A k j, right, and jth column which is equal to 1, right, because we have taken the derivative, that is your kth row and jth column. So, delta A upon delta your A k j, right, it is basically we are taking the derivative with respect to A k j, that particular element. So, it will be 1. So, that means your delta A upon delta A k j, your what you call this term actually it will be 1 delta A, and with respect to this your kth row and that element, that is your kth row and jth column, and this should be equal to 1. So, if it is so, that is equal to 1, that means my delta lambda I, this one delta lambda I upon delta A k j is equal to then psi I k then psi j I, because kth row and jth column. So, instead of writing all psi I your psi I phi I, we will write only that your psi I k and phi j I, right, that is kth row and jth column. So, that is why psi I k phi j I, this is equation 33, right. Thus, the sensitivity of the eigenvalue lambda I to the element A k j of the state matrix is equal to the product of the left eigenvector element psi I k and the right eigenvector element your phi j I, right. So, that sensitivity of lambda I with respect to that element A k j is basically product of the left eigenvector and the right eigenvector, right. So, that is your psi I k and the right eigenvector element phi j I, right. Next, the most important thing, this regarding participation factor. This participation factor at the end also we will see some your what you call some couple of more problems, and elaborately I will take a separate thing and I will tell after making this derivation and other thing, and we will take one more example, and again we will come back to participation factor such that in another form, such that there should not be any your confusion in your mind. So, problem in using right and left eigenvectors individually for identifying the relationship between the states and the modes is that the elements of the eigenvectors are dependent on the units and scaling associated with the state variables. As a solution to this problem, a matrix called participation matrix P, which combines the right and left eigenvalues right and left eigenvectors as a measure of the association between the state variable and the modes, right. Therefore, P can be given as P 1 P 2 P n, this is equation 34, right. This is for my reference, right. Actually, P 1 P 2 P n, it is a column vector, and P basically P actually it is a n into n matrix, right, and these are all column vector, right. So, that means in general P I is given as your P 1 I, P 2 I up to P n I is equal to that from the relationship only that psi 1 I, phi 1 I, psi I 1, phi 2 I, psi I 2, phi n I, psi I n. This is equation 35, right, where phi k I, right, that means in general 1 to n, I mean in general it is 1 to n. So, some term should be there, say phi k I, right. So, that means that phi k I is that element on the kth row and ith column of the modal matrix phi is equal to kth entry of the right eigenvector phi I, right. Similarly, your psi I k, the meaning is same, but your definition is just different. The element on the ith row and kth column of the modal matrix phi psi your what you call is equal to kth entry of the left eigenvector your psi I, right. So, this is the meaning. So, and the element p k I is equal to phi k I psi I k is termed as the participation factor, right. So, thank you very much. In much more detail we will come back in the next lecture.